we're discussing the electrochemical series for now, right? And we're discussing. I'll take this time, right? So we're discussing about how reactions proceed, right? And we were discussing about the reactivity, right? The reactivity series in which we're placing the metals as the reactivity. I'm just giving a recap, right? So this is the reactivity series in which we have the most reactive on the top and the least reactive at the bottom, right? I'll share the slides with you people as well. Okay, so these are the reactive, the quite reactive ones. They have slow reactions, but still reactive. Then we have the not so reactive, which have very slow reactions, maybe over weeks or years, right? And then we have the unreactive ones, which are silver and gold usually, right? So we were looking at the reactions and their products. If we react them with water, then we're going to get the hydroxide and the hydrogen gas release. Same as with calcium and magnesium. With aluminum, right, on the contrary, they don't form hydroxides, they would rather form oxides, and for that we need to heat them up, right? So as you can see this assembly over here, that we're heating this iron or this aluminum powder, right, and then we put in some steam in there to make it react. They don't react with just water, they react with steam or very high temperature steam, right? And in case of aluminum, you need to heat it up along with steam, right? You have to heat up the metal as well to make it reactive. And then we have lead, copper, silver and gold, which do not react with either water or with steam, right? Okay, then we have reactions with dilute acids. All these metals have explosive reaction. The potassium, sodium, lithium and calcium, they produce the chlorides, or the salt of that metal, right? For potassium, if it's HCl, then we'll see chloride. If it's sulfuric acid, then we'll see a sulfate salt being forming, right? This is sulfate part of the salt, right? Metal sulfate, and then we have the metal chloride over here, right? And then we have if we have the nitric acid, then we see the nitrate being formed, right? Nitrate of the salt, right? We'll discuss more detail of this in the acid base unit, right? How these and what are the properties of these salts, right? Usually. Then we have again these metals which have decreased reactivity with dilute acids, right? Again we see salts forming for those acids, right? Acidic salts are formed for the metal, right? If it's again sulfate, it forms a sulfate, and if it's nitrate, we get to see a nitrate. And if we have the hydrochloric acid, then we see the chlorides being forming, and these do not have reactions with any other dilute acids, right? Okay. Now, what is a displacement reaction? A displacement reaction in which a more reactive metal is going to replace a less reactive one. That means potassium is going to replace magnesium in a product, right? Or aluminum can replace tin, or you can say iron can replace copper, right? So, or copper can replace silver. So this is what we mean by displacement reaction, that the metal which is more reactive is going to replace a less reactive metal, right? So in other words, we can say this, like let's say if we have a magnesium ribbon, okay, this is what we call as thermite process, right? Now remember this, I put this example, thermite process, I forgot to add this, right? So what is a thermite process? This process is used for fixing rails, right? And why rails, I'll talk about this more in physics. Do remind me when we go into thermal, right? It has something to do with the thermal conductivity. So in this case, we see that aluminum is above iron. So what we do is that we take aluminum powder and iron oxide, right? This is where we have aluminum over here, and then we have iron oxide, right? So in this reaction, to kickstart this reaction, since aluminum is reacts usually at high temperature, so to kickstart this reaction, we're using a magnesium ribbon. We're not using magnesium because it will replace aluminum. It is only there to provide starting heat, what we call as ignition temperature, right? So it gives the ignition temperature for the aluminum to start reacting. Once this reaction starts, this is a very highly exothermic reaction. That means this reaction results in more heat. So that heat will continue this reaction. So what this does, that once we spark this up, it burns very vigorously, right? Very violently. And in general, it forms aluminum oxide powder, which during the flame and during the you can say the violent reaction, it just forms powders and moves away, and what is left is a solid iron piece or molten iron left, right? which solidifies into this bead, right? Only iron is left. All that aluminum powder just burns off on the sides like powder, right? Thin powder it forms on the sides. So why we do use this reaction? Let me get my pen now, right over here. So let's just say we have a rail, right? A rail track which needs to be filled. It got cracked from somewhere, so they replace that little fragment, they cut that thing out. Now we want to fill this up. Usually we have welding as a process. You must have seen for iron we use welding, which is a very easy process in which you give electricity and make melt iron and join things up, right, using molten iron. But in this case we can't do so. Welding is not usable. Why is that so? Because these steel rails are very thick, right? So if you try to heat it up with a welding torch, we would see that the heat would transfer and it would not heat up very quickly, right? It may also cause thermal defects in this rail. So that means instead of repairing it, if you use welding for this, it might even damage the rail track, right, even further. So what we use is we use the thermite process. So what we do is we put a lot of this mixture of aluminum and iron oxide powder, right? We can use magnesium as well, by the way, right? Not just aluminum. Any more reactive metal which can easily react or catch fire, right? Which magnesium and aluminum both can be ignited at a certain temperature. Magnesium being more easier to react, right? So in this case, once we're going to react once we start this, it is going to form molten iron very quickly, right, to fill this gap up. And because of that, since this reaction melts a lot of iron in a very little amount of time, then it can fill up this gap without transferring much of the heat to the track, right? So it has less thermal defects and it can easily fill up this weld gap, right? Although this is not weld gap, but we can say that this rail gap, right? So now do you understand where this thermite process is used? This is called thermite process, right? And this combination is called thermite, right? This combination of iron powder and iron oxide is called aluminum powder, and iron oxide is called thermite, right? TEHERMITE. Oh god, this is very hard to write on this with the mouse. Let me get my pen. Sorry. Okay. All right. Now I've got the pen. Okay, this is called thermite process, right? Okay. Now moving further, right? We have other displacement reactions. This you can do in your school lab once you join back. I'm gonna put this sample for you people, right? We have done this in grade 8, right? In the book as well, yes. We did that, but I think you were absent that day, maybe. You skipped that lab. I distinctly remember you were not there with the lab. When we made this copper sulfate solution, we put an iron bar in there, right? So we placed it and we saw that after a few days, we saw that the color was changing and this happened, right? What really happened, that copper got deposited on this iron nail, right? And the iron from this got into the solution, replacing this. So what is happening in this reaction, that iron is actually replacing this copper, and as a result you get iron sulfate, right, and copper metal deposits, right? This is what we call as displacement reaction. This is just a recollection to tell you, because what we're building upon is electrochemistry eventually, right? So these are just the basic ideas that we have to review, right? This is an experiment you can run, but I do not recommend using copper sulfate at home because this is very poisonous, right? So if you are not cautious with this solution, and if you ingest this, then this is a poison. It's a very strong poison, so it's a neurotoxin, right? So please be careful while working with copper sulfate, even in the lab, right? Okay, so let's do a little bit of a recollection, right? You have this chart over here. Now Hania, I want to start with you, right? First you give me, the second Abdullah, third again Hania, and fourth over here we'll go with Abdullah, right? So Hania, displacement reaction. We see a more reactive metal replacing a less reactive metal in a solution, right? So Hania, do you think lead is going to replace iron? No. Iron is more reactive. Good. Correct. Abdullah, next to you. Lead and copper. Yes. Not probably. I told you that word does not exist in science. Okay. Okay. Alright. Okay, Hania, next. Quick. Iron and zinc. Iron and zinc sulfate. You can see this. No. Yes. You have the table right here with you people. There's a table to look at, right? And tin and copper. Yes. Right? So let's look at the solution. So you guys are right. Okay? Okay. Now moving further. Now this is the more important topic, and I want you guys to keep this in mind while we move into the next one, right? Let me get my highlighter back again, right? Okay. I'm gonna use a color that is more viewable. It makes it too dark, right? Let me get white. Okay, I'll take white. Let's see what the white does. White is not visible. I don't know what's wrong with this software. I'm not using regular. Okay, ink color. Let me take blue. Let's see what the blue looks like. Oh god. Okay, still works. Okay. Still works for me, right? Alright. Now oxidation may be defined by 3 ways, right? 3 ways we can define oxidation. It is the addition of oxygen, right? Addition of oxygen. So that's point number 1, right? We can see sulfur reacts with oxygen to give sulfur dioxide. So we say that sulfur has been oxidized, right? Or iron reacts with oxygen, we call rusting. So the iron is getting oxidized, right? Oxidation is the removal of hydrogen from a substance, right? That means we can remove hydrogen. I've made some examples for you people in the next slides, right? We'll discuss. And the third way we can discuss is the loss of electrons by a substance, right? That is also oxidation, right? Now, can you guys repeat? The first one is, Abdullah? Yes. Hania, second one? Okay. Third one? Loss of electrons. Now, reduction is the opposite of all this, right? Opposite. That means we will see removal of oxygen, we will see addition of hydrogen, and we will see gain of electrons, right? This is what we're going to see over here, right? As you can see, for reduction, we have lead oxide, which we heated up, decomposed, and it formed lead oxide again, but a different version, right? And we get to see oxygen gas being released, right? So over here, lead got oxidized. Another example is over here, which is this sodium nitrate getting decomposed, right? In which oxygen is getting released out, right? Now these are just the examples with the oxygen, so I couldn't find this anywhere else, so I made my own slides for a few slides at this, right? So in a redox reaction, both reduction and oxidation occur at the same time. It is not possible that you see reduction at one point and not the oxidation, right? For example, when hydrogen is passed over heated copper oxide, copper and water vapors are formed, right? So we'll see a reaction over here, right? Now in this case, you see that hydrogen is brought in, right? There's copper oxide which is heated up, right? So copper oxide will get reduced, right? In this case, reduction is happening, right? Because it is losing oxygen. So the oxygen is getting lost, so it will form H2O, water, right? And that water can be detected using this anhydrous copper sulfate. Now the property of anhydrous salts is that they absorb water, and some of these anhydrous salts of transition metals, why we call them as transition metals, because they're color changing, right? They color change, they transit from one state to another, right? So we will see this becoming blue after absorbing water, and excess hydrogen is lost. So this is the test as well, right? This is also the test for your water vapors being formed, right? Okay. In redox reaction, both reduction occurs, right? The water vapor can be trapped by the anhydrous copper sulfate, turning into white to blue, right? So excess hydrogen is burnt. We can test tested by burning, right? So this is the redox reaction in which you had copper oxide that reacted with hydrogen. So in this case, since you are providing energy, right, rather than it is creating energy, right? So once you provide energy, then oxygen is removed. Why? Because hydrogen is going to take that oxygen away, forming water, right? In which you see that copper oxide is getting reduced. Why it is getting reduced? Yes, Abdullah, can you tell me why is this getting reduced? Yes, oxygen is leaving copper, so that is why it is oxidation. Now, reduction. And why hydrogen is going through the state of oxidation? It is because it is gaining this oxygen, right? So redox. Okay. So few examples. An oxidizing agent is a substance which burns about, which brings about oxidation, right? The first example is by adding oxygen to something. For example, in this case we have rusting, right? Oxygen reacts with iron to form iron oxide, right? So it is the gain of oxygen. Okay. A reducing agent, a reductant. Now remember these names: oxidant and reductant. Sorry, this color is not good, right? Okay, this I just had it done, right? So oxidizing agent or oxidant. Yeah, no problem. Okay, I think you guys can read, right? Now a reducing agent, a reductant, is a substance which brings about reduction, right? Anything that is going to cause the other object to reduce is called a reductant. Now remember, let me get the pen over here as well. I forgot to write this over here. That reductant itself will undergo oxidation, right? It will cause the other object to reduce, but itself it would go under oxidation, right? This is reductant. Now for oxidant will do the opposite. Yes, will undergo yes, it is a reductant, but itself you see it is getting oxidized. Why? Because it is taking in oxygen, right? It is absorbing the oxygen, right? So the oxidant will undergo reduction. So remember, whatever the agent is, itself it would go the other reaction, right? If it is an oxidizing agent, it will undergo reduction, while it will bring about oxidation for the other object, right? Oxidation for the other object or the other substance, right? Itself it would get reduced. Okay. Oxygen is an oxidant. Yes, itself is an oxidant. It gets reduced, and we'll see why it is getting reduced, right? How it does get reduced, because it's losing electrons, it's sharing its electrons, right? That's why it gets reduced, right? We'll see the electron one as well. Now again, in terms of hydrogen, as I said, right, this is the hydrogen example, right? So we see removal of hydrogen and oxygen, right, in which MgCl plus 2HCl, right? If magnesium reacts with HCl, we see that hydrogen is lost by the chlorine. So we say that over here chlorine got reduced. Why? Because hydrogen has left it, right? On the contrary, the magnesium is causing this oxidation. So itself it is an oxidant, and itself it is getting reduced. Why it is getting reduced? Because it is actually sharing its electrons, right? But since we're just talking about the hydrogen leaving, so we'll just talk about this HCl that the hydrogen has lost, right? Okay. Now another example of reducing agent or reductant, right, which brings about reduction by addition of hydrogen, right? This is also known as hydrogenation in terms of hydrocarbons, right? I couldn't find a better example than this, right? In inorganic, explaining the no, it's only hydrogenation, right? Carburization is also there, but not in this kind of reaction, right? It is a physical combination rather than a chemical combination. Now by hydrogenation or a hydrogen, you see that hydrogen is added into the system, so hydrogen has been received, so it is reduced, right? So over here hydrogen itself is a reductant, right? it itself got oxidized because of electrons. We'll see how the electrons are working in the next example, right? Now, we'll talk about in a moment the electrochemical cell, right? So in that electrochemical cell, we will see that how loss and gain of electrons are taking place in electrochemical cell, right? But I just gave you like 3 definitions for oxidation and reduction. This is the third example, right? So by removal of electrons or anything that brings about that loses electrons, oxidize, right? So in this case, if you have the molten solution for NaCl, right, in which you have Na positive ions and Cl negative ions in the in this molten liquid, and you give it electricity, you will see that the electrons are taken away from the chlorine, converting into chlorine gas. So you will see chlorine gas coming out, right? Cl2 coming out, and also you will see sodium getting deposited on the other electrode, right? This is the method, a commercial method for creating sodium and chlorine gas, by the way, right? It's a commercial process used for extraction of sodium. Yes, we do, because we have abundance of sodium chloride in the sea and in the hills. So getting sodium as of any other process is very expensive. This is the least expensive method for production of sodium, because we also get chlorine gas for other reactions, right? Although this is a very dangerous reaction, because both sodium is very highly reactive, and secondly chlorine is a poisonous gas. So it's a very dangerous or hazardous process to deal with. We call those as hazmat, right? Chlorine, yes, you can inhale chlorine. For that we have a subject called hazmat, or hazardous material handling, right? Hazmat, right? So these are hazmats, hazardous materials. Okay, now gain of electrons is what we call as reduction, right? So sodium gains 2 electrons and it gets deposited. So this is the gain of electrons that we're having about, right? Okay. Now furthermore, the corrosion of iron and steel is known as rusting, right? Rusting is specific for iron, and you can say for steel, right? Others are called corrosion, right? The word corrosion is reaction of metals forming oxides with water or other thing. But for iron, yes, for iron we call specific corrosion as rusting, right? The corrosion specific, no, rusting is not, no, rusting only occurs in iron. Corrosion occurs in other metals. It's just a name, it's an old name for it, right? Later on we came to understand that other metals also get rusted, so we actually couldn't call that as rusting, because rusting was for iron. So we gave a new name, coined a new term we call as corrosion, right? So corrosion happens in on metals, right? At least in reactive metals, right? Reactive ones. So yeah, there is no difference, right? But the name rusting is given to the corrosion of steel or iron, right? Specifically to this orange compound forming is what we call as rusting, right? Orange compound forming, right? This is what we call as Fe2O3, iron oxide, right? This Fe2O3 when formed, this orange one, is what we call as rusting. Other metals also corrode. For example, we see aluminum corroding. It forms aluminum oxide, Al2O3. Your aluminum windows, after a few years you see white powder forming on it, so that's aluminum oxide forming. That is also corrosion, right? Then we have brass, which gets dull and black, right? It's because zinc is leaving that, so that is also corrosion, right? Due to air, right? Due to oxygen. So corrosion is the reaction in which oxidation occurs due to the presence of oxygen. Okay. Now rusting requires both oxygen and water, and this is specifically for iron, right? In the absence of either, iron does not rust, right? Now this is the experiment that you can do. In the first experiment we have this iron bar, right? We have placed iron bar in these 4 test tubes. In the first one we put a cotton wool and anhydrous calcium chloride, right? Now remember, anhydrous calcium chloride is blue. Anhydrous means water absorbing, right? It is going to absorb water, right? So any water molecules trapped in the air are now going to get absorbed, and this calcium chloride, CaCl2, right, is going to absorb that water, right? Okay, this is CaCl2. This is, you can put copper sulfate as well, white one, right? Anhydrous. Vaseline is wax. You can put any wax. Vaseline is a more specific brand name we use for domestic purposes, right? For skincare, that's called Vaseline. It's commonly available, right? So in the second reaction, since there is no air, dry air, moisture also excluded, so there is no air and water, so this, you see, it's not rusting, right? In the second case, we dipped in boiled water. Now remember, boiled water has less salts. Why? Because after boiling, you see heavier salts, or most of the salts are removed from the water and only few dissolved salts are left, right? So why boiled water? Because less salt means less electrical conductivity, that means less tendency to lose or gain electrons. Yes, because we filled it with water, but right on the top of the layer of the water, we have placed Vaseline on top. This will block any further air to get in, right? We can also clog this, but some of the air would get entrapped. Putting the Vaseline on top or oil on top is going to prevent this, right? If you guys remember, in grade 8, you had one reaction for the photosynthesis in which we were putting oil on the test tube, if you remember, with the plant coming out of it, right? Do you guys remember that? Now Hania wouldn't remember that because he hasn't taken our class. But this oil prevents air exchange. It blocks air exchange, right? Okay. Yeah. Now, slow rusting. In this, we just put in water. Now, air and water are there, and it can, easily exchange oxygen through this water, right? Yes. It doesn't help the air, it helps oxygen to get to the iron, actually. Yes. Okay, Hania, why is oxygen getting into water? Can you give me example? How is, or where do we see the dissolution of or dissolving of oxygen in water? Why is that so important that oxygen gets dissolved in water? Why by nature it is happening? Why oxygen? Or is it possible that oxygen gets dissolved in water? Is it possible? I'm just asking, yes or no. Oxygen getting dissolved in water. No. How do you think the fish survived then? How do you think the fish is surviving? So CO2 and O2 both are water soluble, by the way. If you remember, you were there with the water tank we were dealing with the physics question. Yes, you were there, right? Where I was talking about the shark. Even then I was explaining this biological fact, right? That both oxygen and carbon dioxide are water soluble. Both of them are water soluble. Although CO2 in more quantity and O2 is less soluble, but it is still soluble. Unlike chlorine and other gases, even chlorine, Cl2 is also water soluble to an extent. Reason being, in swimming pools we put chlorine in, right? To disinfect it, because chlorine is, it kills bacteria as well, right? Bacteria and viruses. Yes. Right. Okay, the last one, in which we have dilute sodium chloride, right? We have added some salt in it to make it more reactive in a way that now ion exchange can happen faster, so we can have more of the O2 as well as some of the Cl responsible. But since Cl is more more in the stable than the O2, so it is going to be the O2 reacting with iron, because there is sodium which is also reactive, so sodium will remain there, although this will provide a more better ion exchange for oxygen to be in there, right? So salt water is going to corrode this even faster, right? This was just a little bit about rusting. Now moving further, now how can you prevent rusting, right? So surface can be painted, right? Number two, it can be greased, putting oil on it, right? Or covering it with a plastic sheet, right? Anyway, right? And the next one is galvanizing, right? Or galvanization, right? Galvanization, right? What is galvanization? In galvanization, what we do is that we take iron or steel objects, we dip them into molten zinc, right? We dip them in molten zinc because zinc melts at a very low temperature and iron melts at a very high temperature, right? Iron melts around 1600 degrees Celsius. Zinc probably melts around at 700 degrees Celsius. So nothing is going to happen to iron at that temperature. So we can easily melt zinc and dip it up and pull it out. Once we pull it out, we see zinc coating on top of it. Since zinc is above, right, above iron in the reactivity series, so it will have to react faster than iron, right? So in case anything gets scratched, you will see that it is zinc getting corroded, which is although not much difference between zinc and iron in terms of cost, but if we look at the structural strength of iron, then you cannot make bridges with zinc because zinc is a softer metal and iron is one of the strongest metals you can find after titanium, right? Titanium and tungsten, this is the strongest metal, right, and the most commercially available viable metal that we have, right? So to prevent those bridges from rusting, yeah, so iron being very strong has a problem that it can easily rust and weaken. So to prevent that, we just coat it with zinc, right? And what really happens that this is also known as sacrificial, right? Another name is sacrificial protection, that you sacrificed one metal for the other one, right? It is not just zinc that can be used in galvanization. The word galvanization purely stands for zinc, right? Now this is called sacrificial protection, right? So we'll see another example over here. This is use zinc metal, right, on big ships because zinc is more reactive. That was, my daughter, she threw something. Okay, so sacrificial metal is attached. So this is what we call as sacrificial protection. Remember, the difference between sacrificial protection and galvanization is just the same. Just like rusting and corrosion. Corrosion is the bigger term, right? And rusting is one type of it, right? Same way, sacrificial protection is the is what we call as anodic protection, right? Anodic protection. There are three names for this, right? Anodic protection. Oh my god, right? Protection. Sorry, my spells. Okay. Anodic protection or sacrificial protection. This uses a more reactive metal to protect a less reactive metal one, right? So anodic protection or sacrificial protection is the major thing, is the complete name of the term. One of the example for sacrificial protection is what we call as galvanization, right? Because again, galvanization is an older process, so this got its own independent name, just like rusting and corrosion, right? Both are the same thing, but one is specific to a specific metal. Same way, galvanization is specific to zinc. Remember, the word galvanization refers to zinc protection, okay? Zinc based protection. While the actual term or the scientific term is anodic protection or sacrificial protection. Are you guys clear on this? Okay. Alright. So the context is there. I will share you the slides, so don't worry on that, right? Oh, I'm moving backwards, right? Okay, now this was not that easily, right? You can discard these things. Now we're stepping into electrolysis. So I couldn't find any considerably good slide for this. So what is electrolysis, right? Electrolysis is a process. I got it. Okay. Electrolysis is a process in which I'm going to use a popper, right? Is used to drive a non-spontaneous chemical reaction. Now, non-spontaneous reactions are those reactions which do not occur on their own, right? Those which occur on their own. For example, if you put magnesium in HCl, then obviously it would start reacting on its own. That is what we call as a spontaneous reaction. Immediately starts, right? Non-spontaneous requires some external energy to do so, right? We see thermal reactions as well. So this is an electrical reaction that we're doing, right? It involves the movement of ions to the electrodes where they undergo redox. You see, that's why we were studying redox, because we were coming to electrolysis. In simple words, it can also be called as breakdown of chemical compounds using electricity. Now this is layman definition. This is the IGCSE definition, right? So remember the IGCSE one, just giving you a basic idea of what electrolysis really means, right? Okay, things to remember. Number one is electrolyte. It is the liquid medium it could be a solution or could be a molten salt, right? Remember, both are electrolytes, not just the solutions. We usually consider solutions as electrolytes. Even molten salts are also called electrolytes, right? Okay. Now, the second one is electrode, right? Terminals used for transferring current through the electrolyte, right? To complete the circuitry, right? Now, out of the electrodes, it can be a cathode and an anode, right? So the cathode is the negative terminal that is going to attract the positive ions, right? And gives away electron. That means it will give the electrons to the positive ion to turn it into a metal. So usually metals or H positive ions, right, is going to be formed at cathode, right? Metals and H positive ions or hydrogen gas will be formed. At anode, positive terminal that attracts negative ions or anions, right? Right, anions, not anions, anions. It's called anion, right? And this receives the electrons. That means the chlorine gas is going to deposit its electrons, right, and form chlorine gas, right? These chlorine ions will deposit the electrons, give away, so the anode receives the electrons as well, right? So we'll see the redox. Now, what is standard electrode potential, right, or standard potential we call it, right? Each element in the series that we saw, right, has a standard electrode potential, which indicates its ability to act as a reducing or oxidizing agent. This is also the reactivity, right? Reactivity. So the more reactive metals will have more discharge, less reactive will have less discharge, right? A more negative electrode, this potential, this represents electrode potential, right? I'm using the symbol. Value means that the species is stronger reducing agent and more likely to lose electrons in the reduction, right? In the redox reaction. And the more positive one, more bigger value of this will be a stronger oxidizing agent and we're more likely to gain electrons, right? Okay. Now, this is redox and electrolysis, right? So we have two half reactions, right? We have the reduction half and we have the oxidation half, or you can say the reaction that occurs at the anode and the reaction that occurs at cathode, right? So we can also call this as cathode half reaction, right? And this is called the anode half or anodic half reaction, right? Cathodic or anodic or anode or cathode half reactions, right? So in which cathode reaction you will see that the positive ion is gaining electron and becoming complete, and in the oxidation side or the anode side you will see a negative ion releasing electron and becoming neutral again, right? So this is the example that I'm talking about. This is molten NaCl, right? Now in molten NaCl we have two electrodes which we give electricity, right? In this case NaCl is already in the form of Na positive and Cl negative due to being molten, right? In solid state it is as solid NaCl. In molten state it forms Na positive plus Cl negative ions as liquids, right? We call this as liquid form, right? And this is solid, right? So if we heat it up, this is the problem, right? Once we heat up and we give it electricity, we see that they have made bubbles, but in the diagram there is no bubble. There we see sodium getting deposited on this cathode, right? We see we're using graphite electrode, right? I'll tell you what type of electrodes we usually use and what are the benefits of using those electrodes, right? So we'll see sodium getting deposited, and over here we see chlorine gas coming out, right? Bubbling on the other one. This is the anodic half, right? And this is the cathodic half of the cell. Are you guys with me till now? Are you guys able to understand all this so far? Anya? Any confusions? No? Okay, let's get into the confusing part. Now it gets difficult. No? Okay. So this is the electrochemical series now, right? The one we just saw earlier. So in this I've also taken an image which has negative ions as well. That means if in a reaction you have F negative or SO negative, just like metals replacing each other, the negative ions also replace each other. You will see that these halogens will go later than these ones, right? For fluorine. Now Abdullah will tell me why fluorine is on the top. Wow, the negative ion. How would a negative ion lose electron? Easier to gain electron? No, that's not the case. Why fluorine is on the top? You forgot. During the product table we discussed about electronegativity, right? The ability to not let go electrons. So fluorine is the most electronegative, right? It's the top of the chart. If you remember, the topmost was the most electronegative and the bottom was the most electropositive. So fluorine was most electronegative, and we had francium, right? Francium being the metal being the most electropositive, right? I told you the diagonal that is there, right, in the periodic table. Okay, now these are in which the metals in higher in the series are more negative. That means they were easily reactive and they will easily be oxidized, and metals in the bottom will be less reactive and less easily oxidized. That means they will have lesser potential, right? Okay, this is the potential that is there. As you can see in this potential, lithium is generating the highest amount of volt, right? That is why we have lithium ion batteries which are up to 3.5 volts. I've taken the luxury of taking some pictures from the internet to give you some ideas about the batteries, right? So how do you calculate the potential between two batteries? Now you do understand the lead acid battery, right? So lead has this much potential, and along with it we use lead sulfate, right? Lead sulfate, which in which the sulfate has lower potential, right? So it generates about 1.5 volts in total. Let's just say if I were to make a battery using copper and iron, right? Or let me just take I do think I have this example over here, right? So in the next example we have a battery, right? How we can create batteries using this information, that which metal is having more potential, which has less. So let's just say you have a battery in which you have a copper anode, right? One terminal is copper, the other terminal is silver, right? Now which one is going to be cathode and anode? It is not that I have devised it. This will automatically get formed on its own, right? We have attached a salt bridge which allows the transfer of ions, right? Positive and negative ions through this, right? So we have copper nitrate solution in one and silver nitrate solution in the other one to support that metal. What we say, the moment we connect these two, I'm not giving external power. Remember, this is not an electrochemical cell in which we are giving power. This is a cell which is giving us the power, and on the contrary, right? This is what we call as batteries, right? This is how the batteries work. So the more reactive metal will definitely get oxidized, right? It will lose electrons, right? So the two electrons that copper has lost will go through this circuitry, and we can use those two electrons, right? And once they have lost their energy, those two electrons will come back to this silver electrode, which is less reactive, and it will gain those two electrons to get deposited on this cathode, right? So this is how we calculate the difference. So let's say if the potential of the copper and silver, right? These are the potential written over here. Now if you see, you have silver being plus 0.8 and copper being plus 0.43, right? So we take the difference of these two, right? And we get the potential that would be get generated, right? Are we clear so far? Right? Again, I will share the slides with you people so you can go over these again, right? So nothing to worry about this, right? Okay. Now we have the lead acid battery. This is the common battery which is used in the cars and in those UPS or solar power battery banks, big ones that we're using, right? In which we have one electrode which is made out of lead and lead sulfate, and the other with lead oxide and lead sulfate, right? Once we put in the load, you see that the sulfuric acid is going to react and going to cause a discharge of these two electrons, which we are using as in terms of the battery power provided to us. This resistance represents the load, okay? Now once we start charging it, it does the reverse cycle, right? Now we are the ones who are giving current, right? If you can see over here. Now what will happen? The lead sulfate will release the sulfate ion back into the liquid, right? SO4 ion gets back in there, right? And over here the lead sulfate is losing those two electrons to support this problem, and we will see lead forming back. And that is why you see these batteries gets damaged, that some of the lead after continuously going back and forth, some of the leads get damaged and get settled at the bottom. This is why we see batteries have a limited life, right? And this also happens to much more important batteries. For lead acid battery, the functional year is 3 to 5 years maximum, and 2 years functional if you use it daily basis, if you're charging it daily, right? If you charge it once daily, that means around 600 to 700 charging cycles it can retain, right? So remember, this is also a trick over here that I'll tell you, right? Compared to this, we have lithium ion battery, or this is the lithium polymer battery, right? In which we have this polymer of the lithium, right? This is a solid battery. Since lithium is very reactive, so you see this is, it's a closed sealed battery that you see in your phone, right? In your phones, or the general devices that you have, the watch, Apple Watch, or whatever you have, right? They have lithium batteries in there. And what is happening in this lithium battery, that it goes back and forth, the lithium ions go back and forth from into the polymer and into the oxide, right? Once you give it electricity, right? Once you give it the electricity, it turns the oxide into this lithium carbon graphite, right? Lithium polymer. And once you take the charge back, the lithium polymer degrades, releases the electrons, and then you're going to get back your lithium oxide, right? Now for them, the charging cycles are a lot more. These are in thousands, right? That is why the lithium polymer battery, lithium ion or Li-poly batteries are very long duration, right? They can work up to 8 years, right, before they degrade, right? Reason being, they have better charging cycles and they can survive more longer than the lead acid battery, which has only 2 years functional life, right? So batteries are non-permanent, right? We're trying to create batteries which can stay longer. We have graphene batteries in research, but they are currently very expensive, right? They can survive extremely large charging cycles up to 100 years, but unfortunately extremely expensive to build, because graphene is a very expensive material to make. It's a lab scale thin film of these carbon chains which you see over here, each single one, right? So we have to make single atom chains which are very hard to make, right? That's what graphene batteries are. Now electrolysis of water, right? Now if we give current to water and we get two tubes in which we have two of these electrodes, graphite electrodes, right? You will see that water can be electrolytes in two halves. In one half, the hydrogen is going to get electrons and hydrogen is going to get formed, and you will have oxygen forming up on the other by releasing again water, and water will go back and will cause more hydrogen to form, and again the reaction will repeat. So again you will get oxygen on the other tube, right? Now before I go further, I have a very technical question over here. You see the difference in the volume of these tubes? What is the difference between the volume of these tubes, right? Why we have collected more hydrogen and less oxygen for the same time? Because obviously once we connect this, both electrodes are getting equal amount of current and equal amount of time. Why more gas in hydrogen and less in oxygen? So what will happen is that the reason why these two are having different volumes is because if you look at this reaction over here, you have 2 moles of water, right? But as of response in terms of gas, you're getting 2 moles of hydrogen but only 1 mole of oxygen. That is why the volume of hydrogen is 2 times compared to the volume of oxygen, right? Because it is the molar ratio that still accounts for it, right? So keep that in mind while working on this, right? Okay, moving further, we have 2 of these questions in which we have 2 metals, right? Copper and a metal P, right? The diagram is given in which we have the voltmeter. That means it's a cell, right? Which metal P produces the smallest voltage, right? Is it calcium, iron, magnesium? Now if you remember the electrochemical series, iron and copper are the closest. That means they have the least difference of potential. Calcium, magnesium and zinc are more reactive. That means they have more potential. So the iron answer over here is iron, right? Okay, in the next equation The equation for the reaction between iron 2 sulfate and bromine is shown, right? This is the reaction that is there. Iron sulfate is reacted, and you see that uh, iron sulfate is reduced in a way, and bromine is also reacting, right? So which one is the oxidizing agent and which one is the reducing agent, right? So something that is taking away the oxygen, right? It is giving the electrons to the oxygen, right? That is what we call as the reducing agent, right? That gives away the electron. So that in this case we have Br2, which is the reducing agent, right? And the oxidizing agent, obviously this is the oxidizing agent, right? And why we're calling oxidizing agent, you see more of this, right? Now more oxygen is there. Now it is 3 into 4 compared to just 4 in 1, right? Although we have a huge number of iron differences, the compound is changing from iron, if you look at this, iron 2 sulfate is now getting into iron 3 sulfate, right? So in this case, iron has lost one electron, right? It has lost the electron, so it got oxidized, right? Sorry, my bad. Then this way, sorry, it is the other way, right? The agent is opposite. Sorry, my bad, right? So in this case, it is Br that is the oxidizing agent, and it is the iron sulfate that is the that got oxidized, right? Because iron is getting oxidized over here, and it is the Br that is getting reduced, right? And why? Because it just received the electrons, right? So it is a conversion from iron 2 to iron 3, but we'll see more of the detail of these questions once we're going to go through more theoretical questions, right? These are just the two most difficult MCQs that I could find. The rest of them are much easier to deal with, right? So we'll do those tomorrow.